Okay. Now, this is a laboratory, so please watch your step. Don't touch things that you don't think you should touch, and I will tell you if you're getting close to anything that is hazardous, okay?
There was a nuclear reactor in here long ago. I'm guessing it was...
Yes, back there, that was the target room, and then the pool actually was demolished and pulled out. We've got these cranes that we can move things around so we can put in shielding, and this is where we do high temperature materials testing and research, including we're doing work on these high temperature heat exchangers for supercritical CO2 power conversion. This compact integral effects test oil loop that we've developed, which is a 50% height scaled replica for a fluoride salt cooled high temperature reactor loop. The scaling between the CIET facility here on the left, and this is the Mark I PBFHR design that we've developed. Now this is a pebble bed, fluoride salt cooled pebble bed reactor. Here's the annular pebble bed core. Coolant flows in through the bottom of the core, up through, out, in through a hot well, and then from the hot well it is pumped by cantilevered overhung centrifugal pumps through the air heater and then back up into the reactor. And so that's the loop that you have for forced circulation through the primary system to transfer heat to air that is coming. There's two of these coiled tube air heaters, and there's air ducts that bring air from a GE Frame 7 gas turbine that's been modified for the external heating to these air heaters. The air comes in, flows up, out through the tube bundle, and you'll see an example of a tube bundle, and then back over to the turbines. And that's how we heat the air up to 670 degrees, which is the temperature it goes into the turbine for expansion. Now, the key thing in this design is that we also have passive safety. So normal shutdown cooling, we use the primary loop to extract heat through these air coolers because we can regulate and control flow rates and the heat removal. And it's a good principle for normal shutdown cooling to have the system be active so that you can control, but also so that you've got some diversity because you want your emergency decay heat removal to be fully passive, no electrical power, highly reliable, so that you have confidence that even if all of your electricity is gone, that you'll still be able to remove decay heat after you shut down. And so what you see here are we call them thermosiphon cooled heat exchangers. These are very similar in design to the decay heat removal system that was developed for the molten salt breeder reactor at Oak Ridge, except that now we're removing heat from the reactor vessel, not from the drain tank. But besides that, this is a separate molten salt loop that operates purely by buoyancy forces, purely by gravity. Salt from the core, after you shut off the pumps, salt from the core flows up because it's hot, and then down through a heat exchanger cavities we call DHXs, and then back through the core. And this flow is entirely due to buoyancy forces. Likewise, in this DRAX, direct reactor auxiliary cooling system loop, the salt which is heated in that heat exchanger flows up and then transfers heat to a set of water-cooled thermosiphon pipes, and then it flows back down because it's cold into the DHX. And what the CIET experiment is capable of doing is replicating these forced circulation and natural circulation processes. Again, because if you match these key non-dimensional parameters for fluid mechanics, Prandtl, Reynolds, Froude, Grashof, then in a scaled system you can replicate the convective heat transfer, both natural circulation and forced circulation.
So in a sense, this is like a giant liquid computer. It's computing the way this would work with a different fluid.
And what's really interesting is that this also, you learn a lot. For example, one of the key things that you find when you build a loop like this and actually try to experimentally get natural circulation to occur and stuff, is that if you get bubbles trapped in the system, which when you fill things, you generally do, they can change the behavior. So in this loop, we've got lots of transparent locations where we can see bubbles and where we can vent them from the high places so that we can get all of the trapped gases out after once we filled it. Well, it's really important when you design the salt system also to make sure that it's not going to have high points that are going to trap gas in ways that you didn't expect. And the lessons that you learn in designing and operating the oil loop, particularly because you can instrument it so much better and you can get visualization of the flows and stuff, the lessons you learn make it better, easier to do good design for the molten salt systems, because when you're up at 600 degrees centigrade, it's a different environment in terms of instrumentation.
Transparent pipes and so forth.
Yeah, transparent pipes are
Things
tough
you
to
can
do.
stand next to.
You might get little windows in,
Yeah,
right?
yeah.
I mean, you can put Flibe into a test tube and heat it up and melt it, and you can see it, but you can't build glass glass molten salt loops.
That would be bad.
Well, they'd probably break, and then you make a mess.
So this is a way to visualize flow and learn how the flow is going to work in a pretty forgiving environment.
And furthermore, it's heavily instrumented. So we measure flow rates using Coriolis meters, which are extraordinarily accurate. So all of the flow rates through all of the branches can be measured with high accuracy over a wide range, all the way from the forced circulation flow rates down to the few percent flow rates needed to remove decay heat. Likewise, we've got about 40 different places where we've got thermocouples, so we can measure temperatures with very high fidelity. And we have 16 different places where we have manometer lines that allow us to make very, very accurate measurements of the pressure. And so by being able to measure pressure, temperature, and flow distributions with very high fidelity through the loop, we're able to validate our models that are supposed to predict. Especially, we really want to know how much flow are we getting and what are the temperatures. Right. The scaled height of all of the major heat sources and sinks is scaled to match what we have in the system, and it's pretty close. We had to finalize the design for CIET before we'd completely finished the design for the Mark I reactor. So if, for example, the height of the coiled tube sink is a bit low compared to where our simulated heat sink is, which is simulated with a fan-cooled oil cooler. But they're pretty close, and by using the codes we can actually assess the effects of these distortions, because in the codes we can change these parameters and see what the effect of moving the elevation of the heat sources in sink up and down is going to be. Of course, as you make a loop taller, you can drive stronger natural convection, and you'll have smaller temperature difference needed to move the same amount of heat. So this is the scaling principle behind CIET. And we can run not just steady state conditions, but also we can study transients. That is, for example, if we trip the primary pumps and we're no longer able to remove heat at the same rate that we were before, we can see how the system responds and how the startup and increase in heat removal occurs in the Drax loop. And doing these types of experiments is one of the principal ways in which we've been able to license passively safe light water reactors. So the passive safety systems that are used in the AP1000 and the ESBWR, and in essentially all of the light water reactor SMR designs like NuScale and Westinghouse SMR and mPower. In all of those cases, the way that we validate the simulations or the models for the passive decay heat removal is with this type of integral effects testing.
Now, correct me if I'm wrong, but things like NuScale, their simulated testing is also done with water. They have to use water to simulate water.
It's a big, yeah.
And so you're able to get a higher fidelity here by using this organic fluid to simulate salt.
That's correct. So for water-cooled reactors, some work was done in the past to do scaled experiments using Freon. That's a really bad idea these days, because you know this is a greenhouse gas emitting stuff, and so but the principal fluid that's been used in the integral effects testing to validate our safety models for light water reactors has been water.
And when you use the same fluid to simulate the fluid you want, there's things you can't match, right?
Right. So the principal things that you end up doing, I mean, the reason that we do integral effects testing rather than performing experiments in prototypical reactor scale systems. You know, in principle, for example, a design basis accident for a pressurized water reactor that is evaluated in which we believe the reactors can respond safely is what's called a large break loss coolant accident. Might actually be physically impossible, but you could think about going to a real big pressurized water reactor, the real thing, getting high explosives, strapping it onto the cold leg of the reactor, and blowing that
Taking the
leg,
pipe off.
take the pipe apart, and do the test. There's a number of reasons why that's just a bad idea.
Well, a lot of reasons.
There's a lot of reasons why that's a bad idea. And in general, we want to verify that even under really severe conditions, we understand how reactor safety systems will behave. And the best way, once we're getting into rather severe conditions, is to make use of simulations validated by scaled experiments.
I think that would surprise people, though, to realize that the best way to simulate a fluid is with a different fluid, not with the same fluid. Because your first impression would be, if I want to simulate water, I should use water.
Yep.
But if you want to do a scaled effect, that's not the case.
This is one of the reasons why one of the sets of experiments that we've run, we understand that fundamentally mass, momentum, and energy are conserved. There's copious reasons to believe that that is true. And when you do the scaling of the conservation equations correctly for mass conservation, momentum conservation, energy conservation, you find that these non-dimensional parameters emerge.
Like Reynolds number.
Reynolds number, Prandtl number. If you then scale the boundary conditions so that the geometry is reproduced, what you can prove through experimentation is that actually the fluid mechanics and heat transfer will be matched.
So you've made it the same. So
Right.
by having a reactor vessel that's maybe half the size of the real thing, you can actually have a very accurate fluid simulation.
That's correct. So a couple of things that's generally done in the scaling for this kind of integral effects tests, the scaling, for example, there's an Apex integral effects test facility at Oregon State, which was used to generate data used for licensing of the AP1000. A general approach is that to reduce the amount of electrical power that's needed, you will do what's called area scaling. That is, you won't try to replicate the full flow area. You'll scale all of the different pipes in all of the different regions down to some reduced area. But you preserve then the height effects that occur so that you can preserve all of the buoyantly driven flow phenomena. And this is also something that we've done here. This is a reduced area loop. But all of the heights and all of the losses in the loop match, and therefore the transient steady state response will also match. Now, to demonstrate that the oil actually does match what happens with salts, we've also compared separate effect test data for things such as heat transfer measurements that were made in heated tubes, which is an important way to measure heat transfer coefficient for the design of heat exchangers. And this data was collected at Oak Ridge back in the 1970s, and when we compare it with the data that we collect with oil, we find that the non-dimensional heat transfer coefficients match to within 1 to 2%.
Oh, that's very good.
Which is particularly in this complex regimes of heat transfer that you get between laminar and transition flow, and it matches quite nicely. What we want to do is to identify additional opportunities where we can make direct comparisons between salt and oil to further increase our confidence and convince regulatory agencies that oil does match. But again, it will, just because of the scaling.
So really the big goal of this machine here is to simulate how decay heat is removed from this design when there's a shutdown.
That is correct.
Okay, well, let's go take a look.
That's the bottom line. Here. Okay, now again, everybody watch your step. There's things you can trip on. This loop is scaled to be 50% of the height of an actual FHR reactor, at least our most recent designs for small modular versions. And it's also close to height for what you might find for a liquid-fueled molten salt reactor too, because they'll end up being of comparable size, since you're moving comparable amounts of heat. Now, what you see here is, of course, a whole bunch of piping that's covered by insulation. This is Schedule 10 stainless steel piping. So the first thing is that we have a drain tank. So everybody who likes drain tanks, this is a drain tank.
That's the drain tank.
And we have the ability to pressurize it, to push the oil in,
Push it back in.
and to drain it back down again. And we've done that a couple of times already. Because we have many places in this loop where it's transparent, we can actually closely monitor as we fill the loop with oil. But the drain tank and the filling process and emptying process actually work quite nicely. We've been quite impressed with how well and easily we can control the rate at which we transfer fluid over into the loop and fill it all the way to the top. under the insulation is where we have these 3 of the Coriolis low meters. We have a primary pump right down here. We put it into a different location in the loop for simplicity, because in a forced and natural circulation loop, it runs in single phase. It's the sum of the loop resistances around the loop that gives rise to the balance between pump head and flow rate, or with natural convection, the balance between the buoyantly driven flow from the temperature difference and the flow rate around the loop. So you'll also note here are some large copper cables coming in and exiting.
Resistance heating.
And this is direct current, low voltage resistance heating. The power actually comes right from his cabinet over here, which is a set of solid state DC power supplies that are computer controlled.
Okay.
And we can put up to 10 kilowatts of heat into this loop, which in salt would be equivalent to half a megawatt of heat.
Because
Which is
of that scaling relationship between the oil and the salt.
It's very convenient. And so
Was it just kind of dumb luck that it happened to be so favorable in that direction that we only had to put it...
when you look at how well the scaling works with oil and how convenient it is and how much easier it is to instrument and operate, and all of the things that work really well when you try to perform experiments with oil to simulate these systems, it makes you believe there must be a higher power that has sometimes every now and then smiles down on us.
So how did you learn that this was possible? Was there a student who approached you and showed you some calculations? Because I don't think anybody's done this before.
We'd already known, and it was for just the hydrodynamics, we've been using water as a simulant fluid. Because if you're just worried about pressure drops in fluid mechanics, all you need to match is the Reynolds number and the geometry. And a student of mine was working on making turbulence measurements using something called particle image velocimetry in a swirling flow inside a tube. This was for fusion applications of Flibe, right? And he was not able with his laser to interrogate really close to the wall of the tube where the most interesting stuff has happened with laminar sublayers and stuff. So he switched to using mineral oil in a quartz tube so he could get matched index of refraction. It was working quite nicely. Then one day he came into my office, and this would have been 2006. And the student's name, by the way, is Flibe Bardet. He's an assistant professor at George Washington University now. And he came into my office and said, you know, I was just looking at the properties here, and the Prandtl number of this oil matches the Prandtl number of salt. So maybe we could use it to do heat transfer experiments in addition to the fluid mechanics experiments. And so we worked around and performed the scaling and realized that in fact we could match simultaneously all of the key non-dimensional parameters that come out of the energy equation. You can get, for forced circulation, you got Reynolds and you've got Prandtl, and then for natural convection you can match Grashof. And as soon as we saw that, and that was when we knew that we needed to look really carefully at using this as a simulant fluid for heat transfer and fluid mechanics.
This technique then is developed right here at Berkeley.
It was invented here, yes.
All right, well, that's
it was invented here, yeah.
Another wonderful thing invented at Berkeley, along with energy from thorium.
That's correct. So a few other key instruments, you'll see lots and lots of places where there's wires coming out. Each of these is a thermocouple.
Okay.
Now, one of the important things you need to be careful with, for example, we heat oil going through this annular heater. Where it comes out, we want to know what is the average temperature of the oil. But it's not guaranteed that once it comes out that the oil has been perfectly mixed. And in fact, the oil, depending on how it flowed up through the heater, will emerge at different temperatures, logically. And you want to make sure that it's mixed before you measure the temperature so that you know that you're measuring the temperature which is important for your energy balances, not just some local temperature in the oil that's different from the average. Well, every single place where we measure temperature at the outlet of a heater, what we do is we measure it in two different locations, downstream of a mixer. And by doing that, we can compare those two temperatures and verify that we're not erroneously measuring a local temperature that is different from the actual average temperature. And this is one of the key sorts of things. There's a number of important design principles in making and putting together these sorts of loops that you either learn from experience or you get data that you can't explain, right? So this is one. One other device that you can see here, let me see if I can point to, yes, this is an example right here. You see this clear Teflon tubing, and there's another one here. These are manometer ports. And up above us we have a manometer rack. And by measuring pressure using manometer lines, we can actually directly measure head. And that means that we do not need to do calibration, which would be the case if we were using pressure transducers instead. Now, that's actually a substantial benefit. A part of the reason that we can do it is because in these salt systems, the pressure drops needed to generate flow are very low. There are many systems where it's just not practical to try to measure pressure with manometers because you get enormous head differences when you start and run in forced circulation, right? In the case of the oils, they have this tremendously high volumetric heat capacity, which means that very low volumetric flow rates can move very large amounts of energy around. Very low volumetric flow rates mean low pressure drop. And the evidence for that is that we can actually, over the full range of flows that we're interested in, measure the pressure drops quite nicely using manometers. And the beauty of using manometers is that they can be very, very accurate measurements. And in characterizing the loop, after we filled it, we ran isothermal, room temperature, many different flow rates, and measured pressure drops so that we can characterize the loss coefficients and the flow losses and verify that they match what we want to have in trying to match the actual prototypical reactor design. So those are the three major types of instruments that we have: flow plus pressure plus temperature. In addition, we have the capability to control the loop. So the pumps, and then up above, we'll see in a moment, the heat sinks are actually oil coolers that have fan coolers. Those are all driven with variable frequency drives. And we've been doing all of the testing and showing that we can control the pump speeds and the fan speeds to control the flow rates and control the heat removal addition.
Nuclear energy is thought of as this huge, faceless, unimaginative industry. But that's changing. Breakthrough sat down with some of the leaders and supporters of the growing advanced nuclear industry about why nuclear is still important and what's being done to make it more innovative.
Well, we need to save the world. We need clean energy. We need it to be abundant and affordable.
Nuclear has the wonderful luxury of being the sort of most concentrated energy source available to mankind now.
So I find it as a completer. You need nuclear as an all-encompassing piece of a big energy puzzle.
It can power cheaply all the other economies of the world.
Energy especially, it's the biggest market in the world, and everyone needs it, and hopefully everyone can get it in a clean way.
One of the most exciting things about this new crop of startups and innovators in nuclear is that they're young, often women, and they're attracted to this not because they want a 50-year career at a big company or a national lab, but because they want to solve problems in the world, because they care about humanity, they care about climate change, and they want to have big impacts.
There's a lot of innovation, a lot of creativity, a lot of problem solving to be done that is much more exciting.
We actually can step right into building a prototype and then have plants much quicker than we did originally.
We see a lot of innovation developing right now. There are many companies in this space who want to innovate, who want to make some substantial progress in reactor design. And so we're seeing kind of a culmination of different organizations that support nuclear right now, and also different reactor design companies that want to see innovation and follow kind of the Silicon Valley model.
We need to change the sort of pathway to commercialization so that we can accommodate these new designs, so that we have a more innovative sector. And luckily, there's a lot underway to make that happen right now.
When we've looked at what it costs to build current reactors, it turns out to be enormously expensive per kilogram of steel, concrete, and copper compared to other products like automobiles and windmills. So there's enormous potential to reduce these costs, but we need better technologies and better strategies for building and deploying them.
Aircraft industry is one. If you look at how, instead of airplanes being totally stovepipe built, everything, engines, wings, and all, it's totally diversified across the planet. So you kind of get that focus, that economic, technological focus, that if you're great at wings, you build wings. If you're great at engines, you build engines. Likewise in the nuclear industry.
Biotech, a phased licensing process, address early issues early on. And then we've got commercial space launch. Look at SpaceX, a different model for how it is that you develop rockets that is very quick, efficient, and at SpaceX, the key thing that they do is that they iterate rapidly. So they build, and test. And it's much easier to do that if you're working with smaller reactors and if you're working with advanced reactors that use coolants like molten salts.
Electric vehicles, for example. You have companies like Tesla where people are lining up to buy their cars that haven't even been built yet. And we need to get people that excited about nuclear energy.
You look at the general tech industry, both software but also hardware. These are companies that are making innovations, and they're doing so rapidly by being able to test what it is that they want to deploy and then improve.
This is just the beginning of a new conversation. There is unlikely to be a 21st century nuclear renaissance without first creating a 21st century nuclear industry. To learn more, read our report, How to Make Nuclear Innovative, at www.thebreakthrough.org.